Hello, my name is Sean Woodson, and this presentation is titled Internetworking, Drexel University. Let's begin. Drexel University is a private research institution located in Philadelphia, Pennsylvania. It is home to 25,500 undergraduate, graduate, and professional study students. Drexel's campus is divided into four parts: the University City campus, the Center City Hahnemann campus, the Queen Lane College of Medicine, which is located in East Falls, Philadelphia, and the Academy of Natural Sciences, which is also located in Center City. Over the last decade, enrollment at Drexel University has grown exponentially. The faculty and administration staff has also doubled in size due to the acquisition of new properties and enterprises. This has presented many logistical networking challenges, as each campus and building feature unique infrastructure and physical topologies. This presentation will focus exclusively on the design, implementation aspects, and business models of Internetworking Drexel University. In order to avoid expensive fees for dedicated communication channels, we have decided to construct a metropolitan area network, which will offer enough flexibility to allow new physical connections and new technologies to be used to increase the shared and dedicated bandwidth. The principal objective that has to be accomplished is the redundancy that should provide backup capabilities in case of a fiber break. Other main concerns are network security and space to grow for bandwidth of each connected institution. Internetworking is the practice of connecting a computer network with other networks through the use of gateways that provide a common method of routing information packets between the networks. The resulting system of interconnected networks is called an internetwork, or simply an internet. Metropolitan area networks is a data network designed for a town or city. In terms of geographic breadth, MANs are larger than local area networks, LANs, but smaller than wide area networks, WANs. MANs are usually characterized by very high-speed connections using fiber optical cable or other digital media. In order to handle the project work and secure the correctness and quality of the design, a specific methodology was followed. Number one, design of the network according to three distinct levels: access, distribution, and main network. 2. Writing the specific requirements of the network's components according to each municipality's needs. 3. Indicative cost accounting of the requirements and the overall design. 4. Final optimization of networks design and equipment design requirements. For this project, we implemented a hierarchical network design model. The model breaks the complex problem of network design into smaller, more manageable problems. As you can see, in the three-layered network design model, network devices and links are grouped according to three layers: the core, distribution, and access. Layered models are useful because they facilitate modularity. Devices at each layer have similar and well-defined functions. This allows administrators to easily add, replace, and remove individual pieces of the network. This kind of flexibility and adaptability makes the layer design highly scalable. The network designers consulted for this project often recommended a mesh topology to meet availability requirements. In a full mesh topology, every router or switch connects to every other router or switch. Because there is just a single link delay between any two sites, a full mesh network provides complete redundancy and offers good performance. A partial mesh network has fewer connections. To reach another router or switch in another partial mesh network might require routing intermediate links. For our purposes, we will use the former. Redundant network design enabled us to meet our requirements for network availability by duplicating the elements in our network. Redundancy attempts to eliminate any single point of failure on the network. The goal is to duplicate any required component whose failure could disable critical applications. The component could be a core router, a switch, or a link between two switches. To enable business survivability after a disaster and offer performance benefits from load sharing, some organizations have completely redundant data centers. Other organizations try to constrain network operational expenses by using a less comprehensive level of redundancy. We've accomplished this at Drexel by implementing a ring-shaped fiber path, which will be discussed later in the presentation. Transitions from optical cables to fast Ethernet equipments were made using media converters from single-node fiber to Category 5 connectors. In this way, we will be able to use any router with fast Ethernet interfaces to connect to the metropolitan area network. In computer networking, fast Ethernet is a collaborative term for a number of Ethernet standards that carry traffic at the nominal rate of 100 megabits against the original Ethernet speed of 10 megabits. As mentioned above, we decided to use a single-node fiber for our transport needs. Single-node fiber has a smaller core diameter than multi-node fiber. The small core ensures that only one path is taken, which eliminates intermodal dispersion and means that single-node fiber supports higher bandwidth rates over long distances than multi-node fiber. For security purposes, we've implemented a virtual local area network. As you can see, VLANs allow a network manager to logically segment a LAN into different broadcast domains. Since this is a logical segmentation and not a physical one, workstations do not have to be physically located together. Users on different floors of the same building or even different buildings can now belong to the same LAN. Physical topology was projected to accomplish four main tasks: connectivity for main educational and research institutions, backup capabilities in case of fiber break, and fair access to network resources for all participants in traffic security. In this respect, we chose to implement a ring network. In the accompanying figure, you'll notice a fiber optic ring and 8 individual branches from this ring connecting all involved nodes. On a macro scale, and for the purpose of this project, the ring would be installed between the 3 main campuses: University City, Hahnemann Health Sciences, and Queen Lane Medical, with 4 branches linking each institution to the Academy of Natural Sciences. The selection of the proper business model is essential for the viability and the success of a project. In selecting the equal access business model, the public sector is only the owner of passive infrastructure. Competition is delivered between both telecommunication carriers that operate the networks and content and service providers. The public sector's organization will provide the fiber optics infrastructure in a cost-effective way to the telecommunication companies. The decision to implement a physical ring topology complete with optic fiber paths paid critical dividends in our quest for both optimization and centralization. It also provided 1. Flexibility to extend the participating institution's base, 2. Gigabit Ethernet switches for greater network transparency, 3. Redundancy, which offers a backup path for data traffic, 4. A cost-effective business model that promotes competition and variety. In addition, through virtual large area network technologies, we obtain security and fairness in regards to available bandwidth and resources. Number 2, flexible LAN management and configuration independent of the point of connection to the backbone. Thank you.